Hi everyone, welcome to new video from Nitinol Engineering. This is the fifth and last part in the series Shape Memory Alloy Modeling using Finite Element Analysis. If you did not see earlier 4 videos, please take a look at them first. You can find the links of all the videos in the description box below. In this video, we are going to focus on super elasticity modeling. Software Mark Mentat has a separate constitutive model for that. We will discuss that model in detail and solve one example. We already discussed this in detail in first part, but just to provide high level recap, we discussed a shape memory alloy is a metallic material which can be bent in any form plastically, and then when we heat that material, it will go back to its original form. This unique property of shape memory alloy is a consequence of reversible solid-solid phase transformation, and this phase transformation can occur because of stress or temperature. At low temperature, we have martensite phase which can be plastically deformed, and on heating, martensite will get transformed to austenite, causing the part to go back to its original shape, and after cooling, that shape will be retained. Now, because of this, SMAs have two key characteristics. One is shape memory effect, which we just discussed, and another is super elasticity. In super elasticity, there is no temperature change because the working temperature itself is high, so material is always in austenite phase. When it undergoes large deformation, because of stress, austenite converts to martensite, and when load is removed, again martensite gets converted back to austenite, which results part going back to its original shape. And we discussed some applications of SMAs as well. Mark has 3 material models. We already saw these 2. So in this video, we are going to focus on this structural model. The main reason behind using this model is it is much simpler than thermostructural model. It has less number of parameters, hence it is easier to get those parameters as well compared to this thermostructural model. This slide shows the constitutive model used behind this super elastic shape memory alloy model. This model is based on work of this author. So if you want to read more about this model, you can check out these articles shown over here. This model works only for isothermal simulations, means there is no temperature change. Hence, if we see this stress versus temperature diagram, the loading and unloading cycle will always be a vertical line. And another condition what we have is this vertical line should be on the right side of this AF point on the x-axis. When this line is on the right hand side, it is always 100% austenite. If we see a stress strain curve for this loading cycle, it will look something like this. This is the loading path and this is the unloading path. This is based on multiplicative decomposition where deformation gradient F is decomposed into 2 parts. One is elastic part and second is phase transition part. If we compare this model to thermostructural model, which we discussed in part 1, here we had 4 types of strain and it was additive decomposition. There we had thermal part. Now in this case, temperature doesn't change, so this part is not there. And then we had plasticity part, which is also not here because it is super elastic model. So you can see how this is much simpler version of thermomechanical model. Now the way in which we define these transformation temperatures, that is also changed. In previous model, we always define this MF, MS, AS and AF values for 0 stress. That means these points. And then we define these 2 slope values, CM and CA. But in this case, we will define 4 points which are shown over here. Let's say if we are loading, then this point will be stress at which austenite will start converting to martensite. At this stress, austenite will be totally converted to martensite. Again at this point, conversion from martensite to austenite will start and it will finish over here. Here itself you can see we reduce number of parameters from 6 to 4 and we don't have G function here. That is going to save us even more number of parameters. And this is how the volume fraction changes with respect to time for austenite to martensite transformation, and this is how it changes for martensite to austenite transformation. Hence both transformations have different laws and these 4 parameters used here are shown over here and here. Out of that, this HSA and HAS, those work as a logical operators just to decide which equation will be used. You can think of it as these parameters are going to decide if the transformation is happening from martensite to austenite or austenite to martensite. So in total, we will need these 6 parameters to define mechanical material model. First 4 are stress values, which can be obtained by performing uniaxial tensile test and by observing the material fields, as we discussed in part 1, very similar to that. The parameter alpha can be calculated by performing uniaxial compression tests as well, along with uniaxial tensile test. Over here, this negative sign means compressive stress, and this alpha is used to model a symmetry between tension and compression. Hence, if your application doesn't have compressive loading, you don't have to worry about this. You can just set it to 0. That means the behavior in compression and tension will be exactly same, but otherwise you can calculate alpha using this formula. And finally, we have one more parameter in mark, which is epsilon, which represents the maximum deformation obtainable only by detwinning, that is without transformation of martensite to austenite. This is bit tricky to obtain via experiments. Here we have to perform tensile test of multiple variant martensite and keep on checking at what strain the entire martensite is detwinned. In most cases, there is no need to measure it experimentally. The typical range for this is between 0.005 to 0.1, and mark sets the default value at 0.07, which is good enough for most of the materials. So you can always start with this value, and still if you are not able to get good agreement between your simulations and experimental results, then maybe you can dig deeper into this and perform few more simulations by changing this value. Now let's see how this material is defined in Mentat GUI. Here we have to choose structural model. Elastic properties are defined over here as usual, and then you can see here we don't have option for plasticity, we don't have option for thermal coefficients as we had in thermomechanical model. Only two things we can define here. First is phase transformation stresses, and then control parameters. Over here also first 4 values are important. Now I know you are wondering why we have to define this T0, Cm and Ca as well in addition to these 4 values. This is because you can define these values at particular temperature, let's say at 0 degrees, and then you can perform isothermal simulations at different temperatures. What that means is here you are defining it at this T0 temperature, but then you can perform loading over here as well. In that case, these stress value will be changed according to the slope. But if you measure the stress values at the exact same temperature for which you want to do simulation, then of course these values doesn't matter. Now let's solve an example using this only structural model. This is the same example we saw in part 2. There we solved it using thermostructural model, but here we will use only structural model. This is the orthodontic wire which is fixed at this end, and displacement boundary condition will be applied at this end. We are going to displace it in x direction. First we will increase the displacement linearly, and then again we will bring it back to its original position. And if we see this loading on stress temperature diagram, it will look something like this. The initial temperature over here, we are going to define that as 35 degrees, which should be much more than AF. In our case, AF is 20 degrees. Let's start with Mentat. This model is already available in Mentat. You just have to go to help, go to users guide, and here search shape memory, and you will find this is example number 52. If you scroll down and click on this green play button, the proc file will get executed and you will have this model in your Mentat. I did some changes, so it is not exactly same, but it is very similar. Let me expand all the folders. We have 2 boundary conditions. One is fixed and one is displacement boundary condition. For displacement boundary condition, we are using this table, which is shown over here. The table is defined up to 10 seconds, but we are going to use only first 2 seconds. We have initial condition, which is 35 degrees Celsius, and this is the material. To come here, we have to go to material properties, new, standard, and then over here in type, we have to choose shape memory. Let me delete this one because we already have one. Elastic properties are defined over here. Control parameters are defined over here. We are going with default value of maximum detwinning strain. And phase transformation stresses are defined over here. I defined the stresses at 35 degrees, which is the temperature at which we are going to perform simulation. Hence, value of Cm and Ca doesn't matter. But if you are performing simulation at some other temperature which is not 35, then you have to define appropriate Cm and Ca values as well. Hope that makes sense. Then we have 2 load cases for 1 second each, and finally job card. I have selected both load cases, all the loads. In job results, we are requesting equivalent von Mises stress and volume fraction of martensite. So let's submit the job. And what we are expecting now is as we load the wire in the areas where stress concentration happen, which should be over here and here, the material will start transforming to martensite. It will transform all the way to martensite as we come up here, and then when we unload, it should transform back to austenite, finally resulting in 100% austenite wire. Let's see if that's the case. Volume fraction of martensite, and then let's see. We are loading. You can see martensite is forming in these areas. This is the maximum load and unloading. all the martensite is converted back to austenite. Another interesting way to see this result is history plot. For that, right click over here in result history plot. I'm going to choose a location over here, this node, all increments, and let's plot the volume fraction of martensite at this particular location with respect to time. Here I'm going to choose that location and variable is volume fraction of martensite. Add curve, fit, and we see initially there was no martensite. Gradually it transformed into 100% martensite and again back to 100% austenite. If you like this video, please show your support by subscribing to this channel, which will give me motivation to create more educational videos like these. You can also go to channel's playlist tab, and here you can see all the videos with similar topics combined together. For example, let's say if you're interested in ANSYS tutorials, you can go to this ANSYS tutorial playlist and see all the videos from this playlist. All the codes and files which I use for these videos are also available for you to directly download from this channel's GitHub profile. The link of this profile is given in the description box below. If you have any questions, please let me know in the comment section below. And as always, thank you for watching.